How does the internet work? If it's so decentralized, then why do most people only have the choice of 2 or 3 providers? What is CJDNS, and what is Packet, and what is it that we're trying to do? Today I'm going to answer these questions and many others, so buckle up because this is the first time that we're going to do a deep dive on what is the real Packet vision. Hello and welcome. I'm going to explain to you today some of the core tenets of the internet, how they serve to create a very decentralized network, why the edges of that network are prone to monopolies, how CJDNS protocol is different, and how the Packet project aims to change the way people get on the internet. So how exactly does the internet work? Well, it's a little bit like a huge mail system. When you send data across the internet, that data is broken up into little packets. Why break it up, you ask? Well, you'd probably like to get your email even while you're downloading a large file, right? By breaking everything up into little packets, you can receive email packets while at the same time you're receiving packets of your big download. Now, each packet is a little bit like a postcard. It contains some arbitrary data, that's whatever you want to send, but it also contains some structured data, and that's the address of the place where it needs to go. Like the postal system, these packets are forwarded in a number of places before they reach their final destination, and the places where the packet stops on its journey are, in the internet, called routers. Routers have essentially 2 jobs. First, they examine a packet and determine where to send the packet next, and second, they actually send it on its way. The second job is relatively straightforward, and current technology is already well optimized for this. So we'll focus our attention on the first. The way routers on the internet decide where to forward a packet to is that they compare the destination address to a lookup table stored in memory. But there are too many computers on the internet to store all possible destination addresses in memory, so routers use a technique known as prefix matching. Prefix matching is based on the assumption that addresses from a single internet service provider will start with the same digits, that is, they'll have a common prefix. Like country codes or area codes in the telephone system, prefix matching allows a router to forward packets in the right general direction without caring where they will finally end up. But this feature comes with its own problems. The first problem is that there's no way to avoid central address issuance. Addresses on the internet are issued by an organization called ICANN, who works through their regional internet registries. In principle, it should be possible to use cryptographically generated addresses, that is, addresses which are generated as part of a cryptographic key, and therefore are self-sovereign. But prefix matching requires that addresses exist in groups, and cryptographically generated addresses are effectively random, so they cannot work. The second problem is that even though prefix matching eliminates a lot of data from memory of the routers, it doesn't eliminate all of it. As more and more internet providers emerge, there are more and more distinct address prefixes, and many ISPs have dozens or even hundreds of prefixes which are distinct because they were acquired at different times. While fewer prefixes would be better for the whole internet, the political reality is an endless march toward more. And the more prefixes that are announced by the ISPs around the world, the more memory that must be present in every router. Routers require incredibly high-speed memory because it must process billions of memory lookups per second as it processes billions of packets. So this memory is very expensive, and it's one of the cost drivers in internet routing equipment. But there's more. Because the memory on every router on the internet is nearly full all the time, there's no way that a router can be subdivided. Now, why would you want to subdivide a router? Well, the point of subdivision is to be able to lease resources. Infrastructure is expensive, and for that reason, most places in the world are serviced by only 1 or 2 physical internet connections. So if we are ever to avoid internet monopolies, the only way that this can happen is by making it so that multiple companies can lease parts of the same wire. And subdivision of fiber optic cables is already in common use, but because routers cannot be subdivided, every telecommunications company must still place their own routers in every city where they want to have a presence. To make this easier, there are standardized data centers, places where routers can be sent in the mail, and for a fee, the operator will hook them up on site. But unlike any other kind of tech company, telecoms still can't avoid owning their own infrastructure. Now I want to talk to you about CJDNS. CJDNS is a project which I founded in 2011 to make it easy to set up a network. In CJDNS, addresses are generated cryptographically, so there's no need for a central addressing authority. How is this possible? Well, instead of prefix match routing, CJDNS uses a routing technique known as source routing. With source routing, instead of putting the address in the packet's destination, the sender puts the path to get there. This solves a massive problem because it takes all the decision making out of the network routers. So all they have to do is do what the packet tells them. But it creates three new issues which need to be solved. First, the sender of the packet needs some way to discover the path through the network for the packet to take. Second, we need a space-efficient way to encode that path. And third, when a network link breaks, it's important to quickly get new routes out to everyone who needs them. To solve the first problem, CJDNS originally used a fully decentralized routing system only. This system was based on the ideas from virtual ring routing and scalable source routing. And while the system did mostly work, we realized that it couldn't provide the quality of service which people could rely on. So we began a new direction based on federated route servers. The decentralized routing algorithm remains in CJDNS as a fallback, and a similar routing algorithm is being actively researched and developed in the Yggdrasil project. So what is a route server? It's a service which collects information about the network and provides routes on request. The forward vision of CJDNS and Packet is that people will buy their internet access from virtual internet service providers who operate route servers that allow their clients to find paths through the network. If we can get those paths out to those who are communicating in the network, then the question becomes, how do we represent them efficiently? Network packets have a size limit, and every bit that's used to send the path is a bit that can't be used for data. 120 bits is 1% of the maximum packet size, meaning for every 120 bits of overhead, it costs you at least 1% of your bandwidth. More if you're sending smaller packets. Traditional source routing included a list of addresses for each router along the path, but these addresses are at least 32 bits each, making it way too much overhead. CJDNS solved this problem using a novel system which we call compact source routing. Compact source routing uses variable width encoding to represent each next hop that the packet should take, so that a router with few connections only needs a few bits of overhead, while a router with many connections can still represent them all. And last but not least, how do we resolve the problem of rerouting when a network link goes down? This has long been a major argument against source routing. That once a packet is flying across the network, there is no way to reroute it if a network link should suddenly fail. That packet is going to be lost. But the reality is, packets are lost all the time. One of the key tenets of the internet as it exists today is that routers are allowed to drop packets if they have to. If a packet is dropped and it's not received in due time by its recipient, the sender will simply send the data again. Giving routers this flexibility has made them significantly easier to design, and it is one of the main reasons why internet protocol outcompeted protocols such as X25, which in the 1980s seemed like it was going to be the winner. In the case of a network lapse, it's not important to rescue the packets which are in flight at the time. What's important is being able to communicate the news quickly so the resent packets will take a different path. And it is my opinion that the federated route servers should be able to communicate this information at least as fast as the federation of routers which make up the internet today. And since they all know which of their customers is actively communicating over the now failed link, they can proactively inform them of the change. Believe it or not, the CJDNS technology that I've just described already works and is in use every day, though more as a secure overlay than a bottom layer mesh network. So what does the Packet project intend to do? The Packet vision is to decouple the administrative aspects of network operation from the physical aspects of operating the hardware. The point is so that regular people can own and operate pieces of internet infrastructure with minimal technical knowledge. To do this, we need to enable subdivision of bandwidth and routers. As we've discussed, bandwidth to subdivision is easy, but subdivision of routers requires us to rethink how the internet works. Fortunately, CJDNS and compact source routing has given us the basis to do so. We envision a future where you can put an antenna on your roof or out your window and start making money by providing access to your neighbors. We envision a world where everyone has the choice of hundreds or even thousands of internet service providers, all of whom build their networks on top of a mesh of infrastructure provided by people in our local communities. And most importantly, we envision a perpetually free and open internet with no central authorities and no kill switches. This is an ambitious project, and there is a lot to do. Packet was launched in 2019, and CJDNS was started in 2011, but these ideas go back as far as 2008. We may not be the fastest, and we're certainly not the most extravagant, but what sets this project apart is the timeless commitment to putting one foot in front of the other come war, global pandemic, and whatever else may come our way. I hope this has provided some insight into why we do what we do, and if you want to be part of making this happen, come join us on the chat. Until then, stay awesome, and we'll see you on the next one.